Welcome to the second video of Module 9. In this video, we're going to look at how to calculate probabilities of simple events. Calculating probabilities is very similar to calculating percentages, where we take the ratio between two numbers. And when we calculate a probability, we're going to look at the total number of favorable outcomes, so the outcomes that we want to occur, divided by the number of possible outcomes, so the number of outcomes in your sample set. So for example, we can look at the event of rolling a dice and consider what the probability is that we roll an even number. So there are three possible outcomes that would satisfy this condition. Either we roll a 2, a 4, or a 6. So there are three favorable outcomes out of our sample space of with 6 possible outcomes, and that means that it has a probability of 0.5000. Remember that in this course we're going to be reporting probabilities to 4 decimal places. In this practice example, it says you roll a 6-sided dice twice. What is the probability that the sum of two rolls is 11 or greater? Okay, so the first thing we need to do is look at what the sample space is. So first find the number of possible outcomes. Okay, we can draw our tree diagram. So we have the first time that we roll a dice, which we're going to have 6 different possible outcomes. So 1, 2, 3, 4, 5, 6. Okay, and then from each of those, we'll have 6 possibilities for the second roll of a dice. Okay, so for the first roll of a die, we have 6 outcomes, and for each of those, we get another 6. So therefore, we have 36 possible outcomes. And for our sample space, we're going to write it in set notation. We can roll a 1 and then a 1, a 1 and then a 2, a 1 and then a 3, and listing each branch in that tree diagram, we will have 36 elements. So to calculate the probability that the sum of the two rolls is greater than 11, we need to think about how many of these outcomes are favorable. So let's look at the favorable outcome. So how many of the 36 possible outcomes will lead to a roll that sums to greater than 11? So we can either roll a 5 and then a 6 and then a 5, and then a 6 and a 6. So there are only 3 possible outcomes that are favorable. Therefore, our probability is 3 out of 36, which to 4 decimal places can be reported as 0.0833. It's worth noting that depending on the application, you may see probabilities reported as fractions in lowest terms. So instead of reporting our probability as 0.0833, you could see this reported as 1 divided by 12, which is 3 over 36 expressed in lowest terms. To express a fraction in lowest terms, when you're working on your MyOpenMath digital homework quiz, you'll see that the probabilities will be asked for in fractions in lowest terms and also sometimes rounded to a certain number of decimal places. So be sure to read the instructions and report the probability as requested. This same type of probability calculation is performed when we're working with data. So given data, we can determine how likely something is to have occurred in the past and use that to predict what will happen in the future. So the probability of an event occurring is defined as the number of times that the event has occurred in the past divided by the total number of observations. In this example, it says find the probability of a 30-year-old person living to be 31 years of age if out of 20,000 surveyed, 19,882 lived to be 31. So this is a basic approach that's used by insurance companies for compiling mortality tables. So the probability that someone lives to be 31 can be predicted from what we know has happened in the past. So in the past, we had 19,882 that lived to be 31 out of 20,000 people that were surveyed, and this can be written as 0.994 4-1. Now we have a practice problem. So a person is picked at random from a group of 100 blood donors, and we've broken down the blood type as follows. So there's 4 different possibilities. You can be A, B, AB, or O, and we can see the number of people that fall into each of those blood types. It's always worth checking that the number of people actually sums to what was given in the question. So we can see if we add up the number of people, there is a total of 100 as described above. What we want to do is calculate the probability that the person selected has type A and type O and not type O. So pause your video and calculate each of these probabilities and then check your solutions. So to calculate the probability that a person selected has type A blood type is we look at the total number of people that have type A out of the 100, and we can report that as a decimal of 0.3500. There are 25 people that had type O, so we can say that the probability of someone has type O blood type is 0.2500. And the probability that a person selected does not have type O blood type means that, so there's only 3 other outcomes. If they are not type O, then they're either or B or AB. And to find the probability of not having type O blood type, we would sum the 3 types together. So some of you may have approached this a little bit differently when performing the calculation. I'm going to show one other method, but when we no matter how we approach this problem, we should get the same probability. So the probability of not being type O is 0.7500. So another way of thinking of this problem is that either a person is type O or they are not. And we know that 100% of people will fall into one of those 2 categories. So either you are type O or you're not. And we can calculate the probability of not being type O as being 1, so 100%, minus the probability of the people that are type O. This can be calculated by 1 minus 25 over 100, and reported to 4 decimal places is 0.7500. This example brings us to the idea of complementary events and our very first probability formula. For an event A, the complement of A is not A. Okay, so we define the formula. The probability of A not occurring is equal to 1 minus the probability of A occurring. An event and its complement cannot occur at the same time, and this is known as being mutually exclusive. If events are not mutually exclusive, we cannot use this complement formula. I just want to look a little bit more at the idea of events being mutually exclusive or not mutually exclusive. So for mutually exclusive events, you could think of rolling a dice and either getting an even result or an odd result. Whereas non-mutually exclusive, if we looked at the 2 events of being even or rolling a 2, that would be an example of events not being mutually exclusive because the event of 2 is also included in the event of the result being even. Okay, some other examples, we could think about the weather, and when it's rainy and cloudy, or it can be rainy and sunny. So if you looked at all the days that are rainy and all the days that are cloudy, you would have some overlap. And within that overlap, that's the reason why our events are not mutually exclusive. Whereas when we're looking at the results of rolling a die, you can have even and odd, but our result cannot be even and odd at the same time. It can just be one or the other. So let's work with an example to practice using this formula. So the Canadian Blood Services indicates that about 46% of the Canadian population has type O blood, 42% type A, and 9% type B, the rest of which have type AB. If someone volunteers to give blood, what is the probability that that donor has type AB blood? So the probability that someone has type AB blood is equal to 1 minus the probability that they do not have AB blood, because either you have it or you don't. And if you do not have type AB blood, that means that you either have type O, or you have type A, or you have type B. And we can add those three probabilities together. So 1 minus the sum of those probabilities, so 0.46. Remember, each of these percentages should be expressed as the decimal equivalency to represent the probability. And we can add those all up. And calculating, we find that 0.03 or 3% chance or probability of the person having type AB blood. Part B said, what is the probability that the donor is not type O blood? So the probability of not having O is equal to 1 minus the probability of having O. And we know that 46% have type O blood. Therefore, we would expect that there's a 54% probability that the person does not have type O blood. So pause the video and practice the following question. It says, given the example above, if someone volunteers to give blood, what is the probability that the donor does not have type AB blood? So recall above, we found that the probability of having AB is equal to 0.03. And for this question, we want the probability of not having AB, which is equal to 1 minus the probability of having AB, since these are mutually exclusive events. Now this is equal to 1 minus 0.03 or 0.97. So there's a 97% chance that the donor does not have type AB blood. So this concludes the end of the second video of Module 9. In the next video, we'll be looking at contingency tables and Venn diagrams that are used for events that are not mutually exclusive.